So section 7.3, we get to meet the polygon family, which means we're going to have to know all the names for all the special polygons depending on the number of sides that they have. So let's take a look at this table, and you guys can fill in the names for all these polygons that have the specific number of sides. So we already know that 3 sides is a triangle, 4 sides is a quadrilateral. Many of you probably know that the 5 sides is the pentagon, penta meaning 5. 6 sides, that's a hexagon, and then 7 sides is a heptagon. These two tend to get confused with each other, so try to not get them mixed up. 8 sides is octagon. That's pretty easy to remember because of the octa, meaning 8. 9 sides is a nonagon, and 10 sides is a decagon. And so if you're good with your Latin or any Latin-based language, you can kind of see some of these prefixes relating to the number. Okay, so we skip over 11. Actually, 11 is down here. There is no special name for an 11-sided polygon, so we just call it an 11gon. And we go right to 12. And if you look at how the dodecagon came to be created, the do comes from 2, and then the deca is 10. So 2 plus 10 makes the 12 sides. And you can follow the same rule for the 15-sided, which is the pentadecagon. So the penta meaning 5, deca meaning 10, the gon part for the polygon. So pentadecagon is 15. So notice that we skipped over 13 and 14, so those would be 13 gons, 14 gons. Basically anything other than the ones that I have listed here, you just use the number of sides and then a dash and then a gon. So like 23 gon. Okay, so you need to know all these names. Not only do you need to remember the name, you need to know the number of sides that's related to it for some of the problems that you're going to have to do. Okay, so let's go here. We're going to explore how to figure out the sum of the measures of the angles of a polygon. So let's take a look at the pentagon and the hexagon. If you don't have a formula, what you would want to do is to break up your shape into the least number of triangles that you could come up with. So by starting at one vertex and drawing in diagonals, we can see right here that it's broken up into 3 triangles. So let's explore the number of sides to the number of triangles. Okay, so in a pentagon we have 5 sides, which we created 3 triangles. Over here in the hexagon has 6 sides, and we were able to come up with 4 triangles. So in general, we want to come up with a formula for n number of sides. If we look at the relationship between 5 and 3 here and 6 and 4, we can see that they have the same relationship, and it's a difference of 2. So what we can say is that the number of triangles that can be made from the diagonals drawn in a polygon is always going to be n minus 2. Alright, so that's good. That's telling us the number of triangles. So what are we going to do with that? Well, the sum of the angles in a triangle, we know, always equals 180 degrees. So over here, if we have 3 triangles, we're going to take 3 and multiply by 180. Over here we had 4 triangles, so we take 180 and multiply by 4. And that would give us the sum of the angles in the hexagon and the pentagon. So in general, what we're doing is we're taking the number of triangles and we're multiplying by 180. So to figure out the number of triangles, it was n minus 2. Okay, so here's our formula to find the sum of the interior angles, that's what the little I stands for, of a polygon is going to be n minus 2 times 180. So we're just going to use this formula to find the sum of the interior angles of whatever shape we want. So in this case, for this example, for dodecagon. So if you remember, that's 12 sides. We plug this into the formula. 12 minus 2, we got an order of operations. We do this first. That gets us 10. So 10 times 180 is going to give us 1800. So we have 1800 degrees for the sum of the interior angles of a dodecagon. Okay, so that's the sum for the interior angles. What about the sum for the exterior angles? Well, Theorem 56 tells us that the sum of the exterior angles of a polygon is always going to be a 360 degrees. And notice this little disclaimer here is that we're taking one per vertex. Because if you look at this diagram, right here, this is the exterior angle, right? But what if I had actually extended this going the other way, like that? Well, there's also this exterior angle, which happen to be vertical angles, right? So they don't want you to add up both of these at each vertex. They only want one of these at each vertex. Okay? So pick which one you want, but you're going to add them all up. And no matter how many sides you have, it's always going to be 360 degrees. So let's take a look at why. That's kind of interesting. Why would that always be 360? Okay, so if you notice, right here at each vertex, the exterior angle and the interior angle make a straight angle. So at each vertex, we have 180 degrees. Here, 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 and here. So we have n number of 180 degrees for the exterior and the interior combined. So if we take 180 and multiply by n, that's giving us both the exterior and the interior for each vertex. So if we subtract the interior, which we just got this formula, n minus 2 times 180, if we subtract the interior, what should be left over is just the exterior, right? Okay, so let's do this. Let's actually simplify, distribute the 180, and then distribute our minus sign, and then combine like terms. Notice that this positive 180n and this negative 180n, those are going to cancel out, and we're just left with 360. So this is really nice. So you can have a 28 gone, and the sum of the exterior angles is always going to be 360 degrees. Okay, moving on. Next, how many diagonals can be drawn from each vertex of a polygon? So let's do our exploration again, just like we did before for the sum of the interior angles. Let's start with our pentagon. How many sides do we have? We have 5. How many diagonals can be drawn at each vertex? Well, let's see. Here we go from this vertex. We get one diagonal, and then we get another diagonal. So in this case, we got 2 diagonals. Okay. Let's take a look at the hexagon. We have 6 sides. So how many diagonals will we get? Let's start up here. Let's do this diagonal. Oops. Wow, that was a really bad one. Okay. Let's erase that one. Okay, so let's try that again. There we go. Much better. Okay, so the point is, you see that we get 3 diagonals when we had 6 sides. So the number of diagonals at each vertex in a polygon with n number of sides, let's see this relationship. 5 and 2 and 6 and 3. Looks like their relationship is a difference of 3. So we can say n minus 3 will get us the number of diagonals at each vertex. Okay, well, we have n number of vertices, because what you would do is you would keep going around. So over here we would add in another diagonal from this vertex, and then draw it to that one. Okay, whoops, that was kind of bad. And then we go over here, and we look, oh my goodness, well, we already have one drawn, so let's draw another one. Okay, and then we get to this vertex, and both of them have already been drawn, and we get to this vertex, and the other 2 have already been drawn. So the number of vertices is n, so you'd have n times n minus 3, right? So we'd have these 2, those 2, those 2, those 2, and those 2. That's the n times n minus 3. But we don't want the doubles, right? Because we saw when we got over here at this vertex, we'd already drawn this one. So we're counting it twice in this n times n minus 3. So to get rid of the doubles, we're going to divide by 2. Okay, and so when we divide by 2, the number of diagonals we get is n times n minus 3 divided by 2. What's going to happen is you guys are going to get confused with this formula and the sum of the interior angles, because this is n minus 3 and that one's n minus 2, so really watch out with it. Okay, So let's do this as an example. Find the number of diagonals in a nonagon. So in a nonagon, that means there are 9 sides. So we do d equals 9 times 9 minus 3, all divided by 2. And when we simplify that out, we get 9 times 6 divided by 2, which gives us 27. So there's 27 diagonals in a nonagon. You can imagine that you wouldn't want to have to sit there and draw all those diagonals. So having this formula is going to be really useful. Okay, so those are the 2 main formulas plus the theorem about the exterior angles adding up to be 360 degrees. That's what you're going to have to work with in this section. Hopefully that's not too bad for you guys. Lots of computational problems, not that many proofs, actually no proofs. So yay. Okay, we're done.